Hey, wait. 29. Sorry, I better write this properly. Looks 4. Okay. Yep, it is 0.707 times 10 to the power 6 Pascal. Okay, so we have found the axial stress, okay, due to the load acting on the brass. Next, we do the stress X for steel. Okay, so this will be equal to Px over, so this will be E of brass over Young's modulus of steel multiplied by the area of the brass plus by the area of steel. Okay, so this is equal to 5 times 10 to the power 3. Then again, you have 104 times 10 to the power 9, and then divide by 200 times 10 to the power 9, multiply by 0.15, and then we have 0.01, and then plus by 0.01 multiplied by 0.29. So this will yield this will yield 1.359 Pascal. Let me do it again. Yep, 1.359. Okay. So both will be in positive. Okay, both will be positive because if we were to look at PX or AX is holding the structure in tension. Okay, so that is the easy part. Okay. So the bending moment, I mean, when I say easy is because last Tuesday or on Tuesday we have derived this expression, right? I'll show you what these expressions are. So just plugging in formulas. Okay. So the next thing we are going to look at is we are going to determine we will determine
Sorry, could you go back to the last calculation?
last calculation. Yes.
Okay, sorry, I just wasn't certain on how it was written. Thanks.
Okay. You have no question, right? You just want to see it again, right?
I just wanted to see which way the ratio between the Young's moduluses were organized. I didn't want to get them confused.
Okay. The formula will be provided for the term test. Okay, so don't worry.
Okay, thank you.
Okay. Then from here, we are going to determine stress X, okay, due to the bending moments My and Mz. Okay, so basically we have to use, we want to find stress X is equal to plus or minus the n my over iyy multiplied by z. Okay, and then mz over izz multiplied by y. Okay. So before we go any further, right? So we need to find, okay, we need to find the centroid. We need to find this centroid. We need to find this y bar value. Okay, that y bar value is important. Then we can, with knowing that y bar value, it will help us. So the y bar value relative from here, this is our y bar value, is our a value. Okay, then we can calculate the moment about z caused by px. Okay, without that, or ax, without that, we can't do anything. So the first thing we're going to do is we're going to determine the position of the centroid y bar, and at the same time determine izz. Okay, so let me get the cross-sectional view. So for this case, okay, this time I will use the reference material. Okay, the reference material used is brass. Okay, you can pick steel. The answer is going to be the what? It's going to be the C. Okay, so we know that this is the brass. This is made of steel. Okay, so we are going to go into section. Okay, so any section horizontally based on this orientation is known as a flange. Any one that's vertical is what we call a web. So I'm going to call the section flange. And then we have the next one, known as web. So the next one that we're going to have, we have to specify the material. Okay, so we know the flange is brass. And then we know that the web is made of steel. Okay, so next we will have to determine the N. So E of brass over E of brass, this is straightforward. This is equal to 1. Well, steel, you have 200 over 104, right? So that's your N. And then the next line we're going to write is the N multiplied by width and then depth. So the axis we want to find is ZZ. Okay, so this is our ZZ. When that's the case, this is our width. And when that's the case, this is our depth. Okay, so for this case, the width of material 1 is 1 multiplied by 150, and the depth is 10. Okay, so this will be equal to 1500. Right, that's straightforward. Then the next one, the N is equal to 200 over 104. The width is 10. The depth is 290. Okay, so 200 divided by 104 multiplied 10 multiplied 290 is equal to 5.577 times 10 to the power 3. And then the next thing we have to do is we want to determine the y bar, okay, from top. From top means the datum is at the top. Okay, so i.e. over here at the top, right? Y is equal to 0. So the individual centroid, so the individual centroid is here. For the flange, and then over here for the web. Okay, so the first one is 10 divided by 2. The second one is 10 plus by 290. Okay, 10 plus by 290 divided by 2. Okay, so it's 155. Then finally, like before, we're going to do in W or with depth and Y bar. Okay, so 1500 times 5, 10500, and then 5.5 cents about 3,155 is equal to 864.435. Then we do a summation. Okay, so you have 1500 times by 5.5 cents about 3. You got 8.3655 times 10 to the power 6. Let me do it again. 1500 plus by 5.5 cents about 3. I think I got it right. 7.077. And then the next one, 1050 plus by 864.43553 is equal to 871.935. Then finally, we can find our Y bar, which is 871.935 times 10 to the power 3 divided by 7077. So it's equal to 123.207 millimeters from the top. Okay. So once you have this now, you can, what I'm going to do is I'm going to calculate the second moment of area, IZZ. Okay. Then we will calculate then we will go back and calculate the moment about Z. So let's sort out our second moment of area first. Okay. So second moment of area. So now we want to do IZZ first. Okay. So IZZ for brass. Okay. Or for the web. Or sorry, for the flange, which is made of brass. So it's equal to width is 1 multiplied 150. The depth is 10 cubed over 12. Plus by the area, this is 1500, right? Multiply by 123.207 minus by 5, the whole thing squared. Okay. So 123.207 minus 5 squared times the 1500 plus by 150 times the 10 power 3 divided by 12. So it's equal to 20.972 times 10 to the power 6 millimeters 4, or it can be equal to 20.972 times 10 to the minus 6 meter 4. Then we look at IZZ for the web. Okay, so we have to include the end, right? So we have 200 divide by 104, multiply by the width, multiply by the depth. Then we